Okay, well, let's do a little bit of deep analysis. Now, this is a cross section,
Okay.
of the coil.
So I have the coil and then I made a cut.
Yes. So if you have a coil, right?
Hmm.
And let's say, and the coils are here, they're coming out and going around, right? So here you have your coils.
Yeah, that. I mean, I made a cut so I can see those conductors cross-section view.
Cross-sectional view.
Yeah.
So this is a, yes. Cross-sectional view. So these are your, this is a wire, for example, one wire.
Yeah.
Right. And then you can think of this coming out.
Yes.
And going back in.
Going into.
This, right? So now here, if you look at the DM, right? So DM
is the mean diameter
of
the coil. Because coil has got some layers.
Exactly. Otherwise, we'll have to take into account each and every one of these coils and then integrate over the area, right? So then here we say, okay, that's mean diameter of the coil, right? DM. Now then, cross-sectional area, A, we had that in the equation before, right, is equal to pi r square. So r in this case then will be dm over 2 square, right?
Yeah.
So dm squared over 4.
Yeah.
Okay. Now, remember our equation Vm is equal to 2 pi n, I think, A f Vm.
Correct.
Right? Now, when we substitute this into this, okay, we get Vm is equal to pi squared over 2 frequency dm squared, number of turns, and b.
Yeah.
Now, according to this, if we increase dm, because it's, it's proportional to the square of dm, we can increase the diameter, but it's going to be large and heavy. Now, as you said, it really depends on the application, right? If you want to measure something really small, that's force.
So the
make it really big.
Correct. The coil has to be in that size.
That size. But then again, you need to consider with that size, will we get
sufficient voltage to measure.
Number of turns, same thing, right?
Yeah.
If you increase the number of turns, or forget about capacitance, you will also have a heavy device.
Yeah.
Imagine 100 turns of wire.
Yeah.
That's going to be a heavy device.
Yeah.
So you don't want large and heavy. But if you look at this equation, those are the things that will give you high voltage output.
Correct. Just in the cross-section area, some pi is missing. Pi dm square by 4.
Pi. Yes, correct. Yes. Pi cannot just disappear like that. So,
yeah.
Yes, pi r squared. Right? Yeah. So this is. Right. So, now, fine. Now, this is just an example to show. Here you have the diameter of the coil, right? And here you have Vm.
Okay.
And here you have...
what are these lines?
Lines are for different number of turns. Okay. Right? So you can see, for one, if you take, a diameter of 5, if you have 1 turn, your voltage output will be very, very low. Right? And obviously, when you increase the number of turns, right,
it's keeps increasing,
right? Okay. Basically, just to show. This graph is from this source. And basically, they did some experiments with different number of turns, right? But they also took a magnetic field times the frequency product of 1 nanotesla hertz. Okay, to get this, and then they change the number of turns and measure the output.
Okay.
And it's clear, right? So obviously, as we said before, now if you increase the diameter a little bit, you end up getting some voltage out. But you cannot have it too small. You cannot have a very low diameter and a low number of turns.
Then it is good for nothing.
It's good for nothing, right? So you basically get nothing here, or something very, very small. Again, just an example.
So one can use this plot to find out. Suppose if I want, let's say 100 millivolt output for a desired value of B.
Yes.
I can decide, okay, what's the probable area and the number of turns.
Yes. So let's say you want a certain output, right? Here.
Yeah.
And based on that, you can kind of draw a graph here.
Yeah.
And see what kind of diameters we're working with. Right? But for that, as you said, you also need to know what kind of magnetic field we are measuring.
That we are going to measure. Yeah.
So based on that, you can probably do some experiments, draw a graph, and then decide the diameter and the number of turns of the coil. Now, we talked about the number of turns, but Bobby, in reality, I'm sure you've wound a coil before.
Yeah.
Can you wind it perfectly where there's no space between the wire? Let's say you're talking about, maybe you can do that with, let's say, 5 turns or 10 turns.
Yeah.
But if you're talking about 100 turns.
Yeah, why is that possible? This kind of winding will not be 100% uniform. There will be some gap. Also, the wires are insulated. So that insulation thickness will definitely come, right? Even the variations in the insulation thickness, all those minute things will come into play, right?
So, and that's what happens in reality, right? So when you wind a lot of turns, you will have some space between the wires.
Yeah, that is anyway will be there because it's round in shape. So
round in shape.
Yes.
So, in fact, you see that the number of turns, right, is actually the number of turns is related to something called a packing factor.
Correct.
How well
Correct.
you wind that coil.
Yeah.
Right? So you cannot just say 100 turns doesn't necessarily mean it's 100 turns in the sense that there's also a packing factor to be considered. Okay, so that's what's shown here. So
or if you have a given area, and if it's a round shape for the cross section of the wire, there's a maximum packing density that is possible.
Yes.
Because there will be air gaps like this.
But so what I've shown here is one way of winding a coil. There are several ways, right? In this, for example,
you can shift it by maybe
exactly,
but then you may lose half a turn or something.
Yes, but in this case, see, this is on top of each other, right?
Yeah,
one on top of each other. Here you have some space.
Correct.
And if you, let's say, change it to so that you wind that wires like this, you still have a space. But in this case, these spaces are equal, but not always, right? There are so many other ways of doing it. So that's something you need to consider. So
N is the number of turns.
AC is the conductor area. Okay. So N times AC is basically the whole conductor area, right? So that means the number of turns. N times, in this case, if you consider here the diameter of the wire is D, right? You'll get something like pi.
D square by 4.
Exactly, D square by 4. Now here is the total area we are considering. What's the total area here?
Total area is L into...
L into, yes.
You are not given the width of the winding.
But let's say, if we know this is, let's say, for example, you're right. Let's say we consider this. Now forget about the mean diameter, all right? Let's say we consider this the outer, and let's say we consider this the inner.
Yeah.
Then the outer minus the inner.
D out by D in
will give you divided by 2.
will be the width of the winding.
Exactly. Right. So it will be d outer minus di
Into L.
into L.
L will be the,
This is L here.
yeah.
Into L.
So this is the packing density.
Packing density, which we also need to consider when we are designing a search coil. Now, in this case, if you just, this is one example. Now, the students can obviously Google packing factor, and there's actually a lot of information when you wind wires, how different techniques can reduce or increase the packing factor. So for this, Boby, it's interesting because now if the wire size increases, the packing factor increases. Yeah. Now, if you take this, right, let's say we are still talking about wire with diameter d. Okay. So then we have this whole area we consider here, right? Let's say the area square, right? In this case will be 2d squared, right? So let's say...
So instead of circular shape, you have conductor with square cross-section area.
Yes.
And then the packing density will be more.
Yeah, correct. Right? So, I mean, here if you consider 2d squared, right? Because this is d over 2 here, d over 2, right? If you consider the same situation here, same here, right? Then you have 2d squared.
Yeah.
Okay? So then you have 4d squared. Correct? Now the area of this. Now, but what we want to find out is this space, right? But if you look at the wires here, it seems that all these, these 4 here, 1, 2,
all that together will be 4d square.
Exactly.
Yeah.
All that will be pi d square, no? Area of the circle.
Pi d square is that shaded portion.
Yes, the shaded portion will be.
While 4d square is the area of the square. Yeah.
And now again, if we take the same thing, no? Pi d squared divided by 4d squared, right? Which is your packing factor, right? Is pi over 4, which is 0.785. Right? So if you wind your wires like this, right?
This is what you can get.
This is your packing factor. Now again, this is just one example, right? So another thing to consider when you're designing a search coil with sensors. Okay. Now, one of the other parameters we need to consider is the DC resistance of the coil, right? Remember
R coil?
R coil. Before we
have just mentioned just R.
I think we mentioned R and also R coil, and also R1.
Okay.
But
so maybe we have to stick to one.
Yes, I think we have to stick to one. So when we talk about just simple R, we're talking about the coil resistance of the coil.
Correct.
Right?
Correct.
So here, let's now measure the DC resistance of the coil for this situation. Okay.
So based on this rho L by A?
Yes. Inductance coil R. Okay. So then we know that it is what? Rho L by A.
Yeah.
So what is L in this case? L is 2 pi R, which is dm/2, right?
Yeah.
Right. Times, you need to consider the number of turns.
Yeah.
Which is what? L over D.
Yeah.
And the number of layers.
How many are 3?
No, we just say N.
N.
Right?
Okay.
Without using any values.
Yeah.
Then you have N, which is, so here, sorry. So let me say this is 2 pi R. Oh. I don't know if you can get it back, but maybe not.
You will write the last equation alone? But
yes. So I think we said, anyway, rho L over A. We said L is equal to 2 pi, okay, dm/2 square.
Yeah.
Okay. Times, we said L over D, right? Which is what? Which is
number of wires in one
row.
Yeah.
So
Like that, you have n
one row.
rows or columns, whatever you call it.
I mean, we are just, this is just for this one, this
Yeah,
diagram,
yeah,
right?
yeah.
Then you work it out, it's 2 pi dm over 2 times L over D times N divided by pi D over 2 squared, right? So then this cancels, this cancels. Okay, you get 4 rho dm L N over D cube.
This is the resistance.
This is the resistance of the coil.
Resistance of the coil.
Right.
So maybe we'll write R equal to or R coil equal to.
Yeah.
No. What I mean is, there you said equal to.
Here?
Before that.
Here. Yes. So, okay, let's, yeah, we don't want to confuse this.
It's clear. It's clear. It's clear.
It's the DC.
Yeah.
You know?
Coil resistance.
Coil resistance. DC. Coil resistance. Okay. Now, but we talked about
the small d is the diameter of the
small d
wire.
Yes, small d is here, right?
Okay.
Individual diameter, the length, right? And the number of layers. Now, we talked about different components, L, C, R, right? And also, let's say your back end. What are some of the other things that can reduce your voltage, or rather influence this VM or the surge coil output? We have the resistance of the coil, but that contributes to something.
I do.
I think you do. Maybe my question was not clear enough. But there's also something called thermal noise.
Okay.
Now the thermal noise, right?
Thermal noise of that resistance.
Thermal noise of the resistance is something that will influence.
I will get an additional output due to this.
Which is a problem, right?
So, how will we represent this?
Yes. So I think this thermal noise is also called some other names, I believe. Nyquist noise, Johnson noise, and all this. But at the end of the day,
there is some equation for this, no? If we know the resistance.
Yes. So if you know the resistance,
4 kT exactly.
Sorry. Should be O T times VW. Now, we know this.
RL is the coil resistance.
Let's make it RC.
Yeah.
Or just R, right? Because we have R.
Yes.
Okay. T is?
T I know, but this T temperature?
Temperature.
Okay.
Temperature. KB. It's a constant.
Boltzmann constant.
Boltzmann's constant.
Don't ask me to what.
What's the value?
What's
the value? I'm sure you know.
I don't remember exactly. 1 point some.
Yeah, it is 1 point something. It is 1.38.
Yeah.
In times
10 power some
minus 23, right? In what seconds per Kelvin? Something like this, I believe. T is the temperature.
Okay. R is the resistance.
KB we know.
BW
is the bandwidth.
Oh.
How can we represent
nothing to do with the flux density B.
No.
Okay.
Actually, I should write maybe BW like this.
I think it's fine.
Yeah. Bandwidth. But how do you represent bandwidth? I mean, that's what the frequency. I mean, if you draw a graph, I mean, I'm sure the students know about the band, but
yeah, I think they have learned the filters.
So then they should know the bandwidth, right? But that's what it represents here, bandwidth of.
So if your system has a very high bandwidth, this component will be there for all the bandwidth, correct?
Yes.
Okay.
He cannot get rid of it.
Yeah.
It will always be there.
What will happen to this? I mean, due to this, there is some output due to this. But what way it will affect me?
Well, now, let's say now, if you have no magnetic field,
there is some output.
There's some output.
Oh.
Or if you're trying to measure some very small magnetic field, right? This output might mask.
Oh, okay. Yeah. So I cannot resolve quantity smaller than this. Yes. So my resolution will be affected.
Got it. Which is a problem, right?
Yes.
So then you need to consider all of these things, right? Because you want to minimize this, ideally. Yeah. So when we talk about that
may be difficult. You have only thing what we can do is probably the bandwidth.
Here, no?
That's the only parameter that we can adjust. I think.
Well, if you look at here, right? I mean, you can think about
value of R and bandwidth.
Yes, value of R. Yeah, or here, right?
Yeah.
Yes.
And maybe keep at very low temperatures, specialized.
But now it's getting complicated,
control
right?
room, yeah.
But I believe because the search coil is used in so many different applications, I get the feeling that you're right in the sense that you can probably only play with the bandwidth and R.
Yeah.
Right? I don't think temperature is something that you can control in that much here if you're using it in a wide variety of applications. And that's where, for example, a squid, right? You have to use, kind of nitrogen or cooling. So your applications are very limited, right? So in this case, I think you can only play with R and BW. Yeah. So there's one more thing, Boby. Okay, so let me erase all this. Now you talked about how this will affect our output, right?
Yeah, resolution we were talking. Yes.
Let me erase all this.
So if the bandwidth will be limited by the RLC components.
You're going back to that now, right?
Yes.
So then in that case, bandwidth is limited by that. So now you can see there are trade-offs, right? You cannot just go wind a coil and then
say take it.
You take it. So it's not that simple. But you also said, how will this affect our output? Now, when we talk about output, right? There's something called signal to noise ratio. Right? We talk about, right? So in this case, SNR ratio. In this case will be your voltage output, right? To your ferrol noise.
Yeah.
Right, correct? Now, if you remember, we already have the equation for VM. We already have the equation for VT.
Yeah.
Now, what happens if you, let's say, right, F, and then we had DM squared, we had L, N, and H.
Correct.
Right? We are still working with
what is H?
H
instead of B.
Instead of B.
Okay.
So in case. Then we have what we just talked about before. Your 4 kb Boltzmann constant, temperature, coil resistance times the bandwidth. Okay. So you have your VM here. And
so this 10 power minus 7 came from where?
10 to the power minus 7 is your mu 0.
Okay. Yeah. So you derived conserving all this.
Yes, magnetic permeability of free space, and then you get something like this. Okay. And then Vt is what we just talked about, right? 4 kV TR bandwidth. And then, you can do some, cut some symbols out, right? Get pi cube to the minus 7 F H square root of EM cube times L times N times D divided by 2. No. Bandwidth. So,
denominator KT, is it
KBT?
KBT? Okay.
KBT, what was it again? KBTR, no?
Yeah.
No. What we did was, rho is there. From R equals rho LOA, right? Remember. So basically, okay.
Got it.
Good.
So that is placed there.
That's placed there. Yeah.
Okay.
So I actually encourage students to solve from here to here.
To this time.
Yeah. It's actually not very difficult.
Got it.
So basically, you remember the RL, right?
Yeah.
That
for that
we worked out before.
Yeah. RL or just coil reference.
Again, sorry.
So they had some expression.
Yes.
If you put that, then
so previously we worked out what R is. So if you actually substitute R here, right, and then you get something like this.
So numerator we have D cube, L, N, and small d. That's the diameter of the wire. Denominator. Sorry, numerator.
Numerator. Yeah. Yes. Number of turns. Number of layers. Sorry.
Yeah.
Diameter of the wire. Length. Dn cube.
Yeah.
H F. Of course, those things don't matter. So what does this show us though? SNR is proportional to the square root of L. Right? Dm cube 3 over 2. Okay. This. And
Yeah.
So before, remember when we started out, I asked you a question. How can we optimize? And you said change the diameter and change the area. But now we have several factors that we need to consider if you want to optimize your signal to noise ratio. So ideally, I think it still comes down to this, right?
Yeah.
Which has a large influence on your SNR. So diameter, but then diameter means you're coming up with a larger coil.
And the denominator, which is B bandwidth.
Yes.
Yeah. Yes. BW.
So again, as you said, if you decrease the bandwidth somehow, but then that depends on your RLC parameters, right?
Yeah.
So
we want this value to be very large.
Yes. Ideally, we want the signal to noise ratio very large, which means we can use it to detect very small magnetic fields.
So that way, numerator has to be very large compared to the denominator.
Yes. You want a large denominator and a small, large numerator and a small denominator, right? But as you can see, there are so many kind of variables, parameters that you have to play around with to increase this SNR.
And F is the frequency of the B that you are measuring.
Yes. That's the time varying magnetic field that you're measuring with the surge coil. That's the frequency of that.
Suppose if the magnetic field is DC, then no output.
Yes. Because now you're going back to Maxwell's equations, right? Correct. Then now you will not be obeying Maxwell's equations if you're out.
Dou B by dou T is 0.
Yes. So for DC fields, again, I think we'll study this later, come up with a different way of doing it, of sensing DC fields.
So a lot of details.
Yes, I think in the start of the course, you talked about will students learn how to design sensors, and I think this is a good example of some of the things you need to consider if you're designing a sensor. And really, I think if you just look at it, a surge coil, you might think it's just a coil, right? But you can see now There are so many things
one needs to consider.
One needs to consider when you're designing. So there are, of course, as we go along, we'll see there are more things you need to consider, but also ways that you can optimize your output as well, right? Because this is not just showing you the problems, but different ways to overcome those and address those problems.
Very nice.